Hello, my name is Lucas Vatsek, and I am a newly graduated senior at the University of Pennsylvania, having studied finance, computer science, and a minor in math. I am the founder and outgoing president of Penn Aerial Robotics, the university's competitive UAV team that travels around the country to participate in various types of competitions, both multi-rotor, fixed-wing, and others. As part of this team and as its president, I helped lead the team throughout several competitions, and I helped push for this competition as well prior to graduation. My role on this team was two sides. First of all, from a management perspective, organizing the team, making sure we're able to participate in the competition, making sure we have the right people, the right technical expertise. But also from a technical standpoint, I designed a lot of the technical aspects of this UAV that we're using. I helped decide whether we're going to use a fixed wing or a multi-copter UAV. I helped create a lot of the software stack that actually runs on top of this platform, as well as the overall system design as far as the electronic hardware goes. I'm also providing technical expertise running up to the competition to the team, even though I did just graduate. And if I am able to attend the competition, then I would mainly serve as a overseeing role and providing some advice and leadership to the team as needed.
My name is Damien. I'm a first-year student of physics and systems engineering. I have been on the team for a year and participated in 3 separate UAS system designs. For this competition, my main responsibility was the navigation system, including obstacle avoidance and guidance. Before the competition and during the competition, I will be responsible for making sure that the ROS system runs smoothly.
I'm Eddie. I'm a sophomore at the University of Pennsylvania right now. I've been on the aerial robotics team for 2 years. I served as treasurer this year, and next year I was recently elected president. As far as the AUVSI competition, I serve as team captain, and I worked on the cybersecurity as well as making sure everybody had things to work on and helped out with any issues. So AUVSI will be my second competition, and I'm really looking forward to it.
Hey, my name is Vanek Karaher. I'm a sophomore in mechanical engineering, and I've been on Penn Aerial Robotics for a year. I'm currently lead mechanical engineer of the team, and for AUVSI, I designed the air delivery system.
Hello, my name is Derek Nong. I'm a freshman studying physics and electrical engineering. For the AUVSI competition, I was in charge of making the ROS interoperability node, which allows us to send and receive data from the interoperability server.
My name is Stephen Irely. I'm a computer science student, and I'm also a freshman. My experience on the team has been primarily with the AIA DBF, which is building a foldable fixed-wing drone, and I did a lot of work on SolidWorks for the different parts and 3D, particularly the 3D printed parts on the team. But now, particularly with the AUVSI-SUAS, I am doing more of a software role, and particularly I'm focusing on the ground station and the interoperability station.
We've chosen a multi-rotor platform for the competition, specifically a hexacopter. We felt the accuracy and maneuverability of a hexacopter is a great asset. Specific advantages include the ability to hover before dropping the payload and VTOL capabilities. The frame is a modified DJI F550. The modifications include longer arms, allowing for larger props and motors. This change drastically increases our maximum lift and allows us to fly the UAV within the efficiency ranges of the motors even while carrying the payload. On the software side, we use a Pixhawk 2 as our flight controller. This was chosen due to its easy integration with ROS and off-board and autopilot capabilities. The Pixhawk can already fly through waypoints and enable geofencing without any custom code. The Intel NUC does all the heavy lifting for processing. Sporting an Intel i5 processor, there's plenty of power for real-time image processing on board the hexacopter. Commands are sent to the UAV through ROS commands. ROS allows us to be program agnostic using both C++ and Python. We've implemented code to perform every aspect of the mission. However, full stack testing has demonstrated varying levels of success. To obtain confidence ratings, we asked each team member to rate the likelihood of successfully completing each mission component on a 5-point scale, if the competition date was today. These were later converted to percentages and are currently displayed. Due to Pixhawk supporting waypoints, we are confident in our ability to accurately approach waypoints. Furthermore, our payload deployment system has been proven to be reliable, and the UAV can further increase accuracy by accounting for local conditions such as wind speed and direction. Although the interoperability system is stable, we cannot guarantee that it is able to handle all potential networking or communication issues. For obstacle avoidance, we are confident that our algorithm is able to calculate a path for static obstacles, but there are always edge cases which may arise during the competition. Unit tests ensured the sanity of our code base. They provided a basic check when refactoring large pieces of code or checking complex calculations were accurate. Due to the nature of UAV development, however, much more testing was required since unit tests cannot accurately reflect the effects of one piece of code on another. This is where Gazebo comes in. Gazebo 7 was used to simulate a real-world environment. A custom UAV model was created to replicate real physics as closely as possible. Thanks to Gazebo plugins for adding ROS supports, the full stack could be simulated using the exact same codebase. Once simulation tests were completed, we tested on the real hex inside of a large outdoor net. The net provided safety in case of a flyaway, providing a secure environment to test experimental code. Once everything worked as expected here, we finally integrated it into the mainline. In total, 12 fully documented autonomous flights were performed. However, many more were completed by individual team members during testing. Each official test lasted for a duration of approximately 30 minutes, which was the lifetime of our battery. Manual flight time was kept to an absolute minimum. In cases such as this, when a large area was required, our flight zone is a park. Due to the park's public and potentially crowded nature, most of the time we took manual control to avoid flying over people or cars, not necessarily because of malfunction. As far as tuning is concerned, we made small tweaks to PID values after each flight if we noticed something awry, such as twitchiness or wobbling. To test the expected accuracy of waypoints achieved by the hexacopter, a list of 100 arbitrary waypoints within a boundary was generated. The hexacopter was instructed to fly to those waypoints while recording telemetry into a Mavlink file. After the flight session, the file was reviewed to determine if any consistent errors appeared during the flight. Parameters were then manually adjusted and the process repeated. In this manner, parameters specific to the UAV could be obtained. The waypoint testing was done in an open field to best imitate the competition conditions. Waypoint accuracy highlights another benefit of using a multi-rotor platform. We have set the parameters such that if we miss a waypoint by more than 1 meter, the hex will turn around and make another attempt at the waypoint. As explained in the technical paper, our artificial potential field algorithm allows us to avoid obstacles live. It's not very calculation intensive, so it can be invoked at high frequencies. The static obstacle avoidance algorithm has shown very high performance during testing and simulation. However, running the code was unreliable during the simulation. This was probably caused by the relatively low performance of the machine which ran the simulations. Nevertheless, for this reason, the algorithm was not tested on hardware. For static algorithms, the static algorithm manages to avoid all obstacles. For moving obstacles, the static algorithm manages to avoid only around half of all obstacles. It fails when it is in front of the obstacle's path. This will be rectified with additional tuning of the algorithm's parameters and the addition of the dynamic component of the algorithm. Imaging is done at an altitude of 50 meters with a 10 by 10 meter FOV. The ordered camera is 1.3 megapixels, which gives a pixel density of 2 pixels per centimeter. The computer vision algorithm detects all of the uniquely colored objects in the frame and stores their position, size, cropped image, and classification. The point of the object detection component is to identify colors that are not usually found in a natural environment. It's fairly accurate considering it only uses color thresholding. The most common false positive is particularly orange soil. The most common false negative is in colors that contain a lot of green, like yellow or teal. The convolutional neural network used for object classification is still being trained. The training data is a set of real images of letters and numbers on signs with the parachute deployment system, the water bottle showed no signs of damage. The 16-inch circular parachute is constructed out of mylar and cotton string. Since there is some difficulty finding a suitable adhesive for the mylar, a new material will be used in later designs. The deployment mechanism consists of a servo that rotates to release the bottle, which is hooked onto the servo arm. While this setup was suitable for preliminary testing, a more robust system using a linear servo will be used to save weight and to ensure the bottle has no way of falling off during high acceleration. Once the bottle is deployed, the parachute is pulled out of a tube and deploys roughly 4 to 6 feet below the drone. Through numerous tests, the system performs reliably. 2 drop tests were performed from a height of 30 feet. In both trials, the bottle survived with no significant damage. One of these trials was filmed and tracked just before the bottle's impact, the results of which are described on the next slide. With no upward trend present in the bottle's velocity, it's apparent that the 30-foot height was sufficient for the bottle to reach its terminal velocity. The terminal velocity in this case is the average of the velocity points collected at 9.6 meters per second, or 21.6 miles per hour. While this terminal velocity is slow enough for the bottle to land without damage, it wasn't slow enough to prevent injury in the case of someone standing below. This safe velocity was determined to be 6.7 meters per second, or 15 miles per hour, in our design paper. Therefore, more testing will be done with a larger chute and a professionally made domed chute to decrease this speed.